It's definitely, yeah. So all you have to do is, frankly, even we see these lectures multiple times because the professor has explained it so well, right? Even like, like he has went it so beautifully that, even a single sentence has got so many meanings to understand there, right? So you will have to watch it
Yes,
again
sir.
and
So
again.
I make, no, sir, make a note what the professor.
Definitely you should do. Definitely you should do make
So
notes
this
making.
can help lots of me.
Right, right. And keep revising, because here you will not get any complex problem. It's just that concept you have to know. That's all. If you know the concept, it's done. And see, there are other thing also wherein you know the concepts. Let's say in maths you have, let's say, some topics like calculus, or let's say some topics like in exponentials and logarithm. Though even if you know the concept, you might find some questions being tricky to solve. Tell
No,
me if
sir,
I'm wrong. Hmm.
it's okay, sir. But every time you taught us this one week one topic,
Yeah.
but every time when we do the questions, we confuse about relations and.
Okay, okay, so the relation thing, you still have doubt in relations.
Nay, I have no doubt. But
Okay.
when we do the questions
So you have problem in,
in examination,
okay,
we every time we do wrong.
okay, okay, let's see. Let's see what we can do. So I'll suggest you to practice a lot. That's the only thing you can have.
Yeah, sir, actually, it is too long to me. I have a around 26 years to leave
Yeah,
my gap in a study.
I get it. Yeah. That's okay. That's not a barrier, I would say. Yeah, of course you will have to spend more time, and it's like you are coming back to academic again, right? It's just that you are not used to it for so many days. You need some times, and not used to it, and all of a sudden you are coming for maths, right? So that is, again, but don't worry about it. That will certainly.
I did my BSc in mathematics, but it
Mhm.
really very long time to me.
No, sure. Okay. Okay. So
Even
now
11th, 12th, I forget everything.
it's okay. It's okay. No worries. But you then certainly you'll have to practice a lot, right? You have to put more effort. Let's
Uh,
say,
One thing, a domain, when we find the domain of composition,
mhm.
it's very tricky. Every time I'm stuck in.
Okay. Okay, don't worry. We'll come up with some kind of session wherein we can help you out, you know, solving this domain kind of problems. But be thorough with whatever you know. Be confident about it. Okay. So okay, let's start our session now. Okay. And as you asked, you have some doubts in DFS and BFS. We'll take up at the end. Okay. So now we can see that today very less of you are joining, maybe because of Holi or something.
Yes, yes,
Yeah.
yes.
So how are you all? All good? How is preparation going on?
Good, sir. Fantastic. Good.
Okay, good. Good to hear this. All right. So could you just join here in peer deck, because this is like more slide oriented session today. So we won't be going to our like normal, the note where we write. So I have some 2 3 questions to discuss there, so we can take up there. So but I want all of you to join here, then it will be good. So 5 of you have joined, and I think we are just like 14 of us, so you can join, take time, join. We can start at 7:05. Okay. So how is like graph theory? Much easier than the other weeks?
Yes, sir.
Much easier, is it?
Easier.
Yeah.
Questions are easier. But
Yeah,
concepts are
yeah,
lengthy to.
yeah, right.
Yes.
Of course, like there are so many things, and you have to keep those many things in your mind. And certainly you'll have to know that concepts. Basically, it's just that once you know the concepts, you can apply it. It's just like relations, you remember, like if you know types of relations, then all you have to do is just stick on to the definition and explore around, isn't it? The
Yeah,
similar
yeah.
way, it's like discrete mathematics, right? So we cannot, and even we are restricted to not frame any difficult kind of questions. So it will be like very straightforward. And since this CT, this part of the maths you will be learning in CT as well as Python later in your courses. So I think there will be a repetition. So don't worry about the thing. But of course, if you need to score, then you'll have to know here in maths. So that will be there. All right. So I can see like some of you have joined. So maybe I can just start and then the others can join us there, right? Okay. So as most of you know how to join, so you have to go to just peer deck and then use this code, which you can see here in the top left corner. Sorry, top right corner, and use that code for joining here. Those who haven't joined, because I can see some of you haven't joined yet, right? So today we are doing this mathematics one. You know, it's like a ritual what we had been doing till now. I know that this doesn't account for your, your final counts, this assignments, but it's good that we keep some kind of decorum in terms of this, like solving some questions with us, right? So that is always good. All right. So maybe we can start our session today. Yeah, please.
Next week there is a revision session.
Sorry.
In calendar, there is no mark of revision session for math.
Okay. So yeah, you will have revision session. Don't worry. We will announce it soon. Maybe you will have two revision.
Sir, there is mock test also for
Yeah.
final.
Yes.
When Sunday or
We'll let you know. Maybe
Coming
we'll try to
Sunday.
keep it on Sunday only, because so that all of you can attend that, right? So let's do. Just give me a minute, okay? So let's start with our session now. So I'll mute you all. So you know how this thing happens, right? So here you have a test problem. How many vertices are there in this graph? It's a simple question, just to see how many of you are participating, or maybe like for you to get acquainted with how it happens, how to participate here in the peer deck, because there might be some who has never joined here in peer deck. So I could see like 17 of you have joined here, not all. So do join here, because this will be really helpful. Essentially, like most of our time we'll be spending here on this slide, so it will be good that you are participating with us and you have active participation. So the session can go that long, and even that will benefit you.
Sir, can I say something? Like, many people on my group are telling that they are not able to join the Zoom meeting. I don't know why.
Sorry, your voice is breaking. You are telling that many people are not able to join this Zoom meeting, is it?
Sorry. Hello.
Yeah, please.
Sir, I'm telling like how many people are telling no, they are not able to join the meeting.
Yes, sir.
So,
Me also. When we attach with my email ID of IIT, then we join that one.
Okay. So maybe I'll just convey this to the team once, so that they can join. Then how did you guys join here?
Hello, sir. They can join from the calendar link given on the calendar.
Yeah, right.
Yeah, many times they do not send the link in the WhatsApp group.
Okay, so they are waiting for that WhatsApp group thing.
Yeah, I
Okay.
think so.
All right. Okay, so but anyways, the formal thing to do is go through the calendar and then do it, right? All right. So you see, like 21 of you are here and 15 of you have given response. So at least yes, all of you have given answers. Maybe this is like first time happening. All right. So let's see how many vertices are there in this graph. So 7. It's just a simple test problem just to see how many of you are giving response. That's all. Okay. And how you should give response. So these are the things. So this is our topic. So today we are just going to start with what is graphs, vertices, and degree. Okay. So these are like some fundamental things, like even you would have observed it when you are dealing with the graphs. So, you know, any vertices in a graph having, so any vertex in a graph having n vertices, okay, can have a maximum possible degree of n minus 1, right? So these are just a fact, right, which you should know, or you can just note it down, these things, or we will provide you this slide. Thereafter, you can note it down. Then you also should note that sum of the degree of all vertices will always be even. This is something you can prove yourself. You can just try drawing multiple graphs and then see it, like how does it happen. But certainly it's just, you can just think of, it's always going to be even, right? Then if two vertices in a graph have degree n minus 1, it means there will be no vertex with the degree 1. This is also a proven fact. You can just try to disprove this statement by taking, yes. Any doubt here? No doubt. It's
Degree
just a fact.
in the sense edge.
Degree, yes. Yes.
Okay. Sir.
Yeah. So,
So?
yes.
So could you please explain the meaning of degree?
Degree is just edge here. It's just that an edge. So for example, if you are to take this, let's say this is vertex 1 and this is your vertex 2, okay? And this is your vertex 3. What is degree of 1? What is degree of 1?
1.
1. What is degree of 2?
1. 2. 2.
2. What is degree of 3?
1.
1. So what do you mean? At least one end of an edge should be there with that vertices, right?
Okay.
And notice this is an undirected graph,
Yes, sir.
right? What if you have a directed graph? Then what do you say? You don't say degree at that point of time. You say in degree, out degree. You never say degree. You say in degree or out degree. That's all. So could you tell me how many in degrees does, so I'm talking about in degrees now. Okay.
2.
So how many in degrees does one have?
2.
Zero.
No,
degree.
0.
For one, it's 0.
So 0.
0, 0.
There's no arrow pointing towards 1. So I think you're on mute.
I'm sorry. I just took a minute of yours. So yeah, could you tell me how many 1 degrees does vertex 1 have?
So in degrees, right?
In degree. In degree is
Degrees.
0.
0.
0, sir.
0.
What about 2?
1.
1.
1.
1 into
What about 3?
1.
1.
1. What about out degree for this one?
For 1, it's
For 1, it is
1.
1.
1
Out
it is
degree
1.
is
It
1.
is 1.
2
For
it
2
is
it is
1.
4 is 1. 3 is
3
0.
is 0.
0.
All right.
Or
So
3
you
is
notice.
0.
So you never say just degree word for a directed graphs. Okay.
Okay.
All right. So that is something, that is what degree means. Now you got it, right?
Yes, sir. Thank you, sir.
Okay. So now this is a simple fact which you have to keep it in your mind. So based on these facts, answer this question. Now we have a graph G with vertices.
Sir, accordingly, second.
Sorry.
Excuse me, sir.
Yes.
Accordingly, we can say that the previous slide that has been shown is based upon the, undirected graphs, right?
Right.
Sum of degree of vertices will be
Right,
that is for the
Right.
directed graphs. Okay, sir.
Correct.
Thank you, sir.
Yeah. So so you have a question on, based on these previous 3 facts, or like any other facts which you know, but essentially those three facts what I have told. So we have a graph. So maybe this graph is not. So we have a graph G with vertices A, B, C, D, E. We write down the degrees of all the vertices in an order A, B, C, D, and E. Okay. Which of the following is the possible listing of the degree? Okay. So now you remember, now we have three facts. Now based on those three facts, or like any other thing which you know, right? Or essentially you can know just by drawing the graph, just tell which among them is correct.
So in this question, we draw the graph on any type of graph.
Draw the graph, or like that is one way of doing it, or you can just simply based on your experience with the graphs you can give your answers. That is also possible. You can do it in any possible. Let's I'll mute all. I'll give you 2 minutes and maybe 3 minutes and try to solve this. Okay. So do you need some more time?
It's done.
Finish.
Done? Finish?
So 1 more minute.
Okay, okay. So maybe we can just wait for another minute. And any of you can raise your hand to explain this. Done?
Yes, sir.
All right. So would you like to explain this?
So I actually drew out all the options.
Okay. So let's see first, what are the popular responses? All right. So three of you are saying option A as the answer. Two of you, three of you A, B, C, but popular answer is D. All right. So let's see. Yes, please go ahead.
So I drew out the options. So for the first one, I connected everything to A.
Okay.
Then I also connected B to everything else. And
You checked it with drawing all of these, right?
yes,
That's why
sir.
it took more time for you. You know, yeah. So we just discussed three facts, right? Remember?
Yes, sir.
Right? So based on those three facts, the solution is here, right? So let's go with the solution. So of course, you can draw the graph and then give the answer. That is one possible way. I think that is okay. What more explanation that is needed, right? So that's okay, Shreya. All right.
Yes,
So, all right. So good that you did it in any, you can do it in, since these questions are not very complex, you know, you can, it's very easy to visualize and do things. So you can do it in any possible ways. All right. So let's see here. First of all, if we can go with the options, maybe I can just tell you here. You see clearly option C is wrong option, right? Anybody can tell me why this is wrong?
So
Any of you?
Because maximum
Total
vertices
vertices
are
are 5 minus
Adjacency.
1, 4.
Yes, yes. Because
4
you
must
see,
be the maximum.
correct. See how many vertices it has? 5 vertices, right? So how many degrees? What is the maximum degree a vertex can have? N minus 1.
N minus
That is 4. So option C is gone. Now
Yes,
go
sir.
with option B. Just add all
2 is
these.
also wrong.
Why
Because
2 is
sum
wrong?
not even.
Why 2 is wrong?
Sum-
Yes,
Sum
because yes,
is not even.
sum is not even. Okay. Could you tell me why is option A is wrong?
There are two.
Yes, there are two
We
vertices
cannot have
with degree 4, right? With degree n minus 1. If that is the case, then you will not have two vertices, or like you basically you will not have any vertices with 1 degree, right? That's what our this third fact was, right? You will have no vertex with degree 1, right? If you have two vertices in a graph which have n minus 1 degree, that is 4 comma 4 you see in the first option, right? It means there will be no vertex with degree 1, but you have two vertices with degree 1, right? So you see this option is gone, this option is gone, this option is gone. So option 4 we can think about. So you can think of all these three facts and then try to solve this. It satisfies all those three facts, and also you can draw the graph and then understand that. All right. So you see it's the same thing written here. Step 1, you see that, you know, why we are ignoring option C. It's just because you have this degree 5, right? But it should have what? N minus 1 degree, which is 4, right? In step 2, we are telling that the sum of the degree. We are just talking about option B, which I explained you, or like all of us explained this. So you see this here, the sum of the degrees turns out to be 7, which is odd, right? Which is not right. Then you see in option 3, which we are looking at option A, here we have even drew the graph. So maybe Shreya, you would have found out that option A was wrong just by drawing the graph. So I think you would have drawn graph something like this, right?
Yes, sir.
Or something somewhere like this, right? So if two vertices in a graph have n minus 1 degree, it means that there will be no vertices with degree 1, right? As you can see even in this graph, right? You see this vertex A has 4 degrees, right? And you see vertex B has 4 degrees. Now you see, do any of these vertices, the remaining vertices, have degree 1? No, right? So this is ruled out. So this is gone again, like first option is ruled out. Then again, you see option 4, it satisfies all possible conditions, right? You can see, and even the graph is drawn. So perfectly, we are happy with the option 4, and that is the right option. Okay. So now we think like that part is okay. Now we can draw the graph. We understood what is the degree of a graph. And then for a directed graph, we just roughly told you what is this. You will not have a concept of degree, but you'll have the concept of in degree and out degree, right? That is something we discussed. Now, you know, as you would have gone through the previous, you would have seen it in the lecture and the previous live session as well. You know, what is this adjacency matrix, right? So what is the typical thing we do? We give you a graph, then we ask you to find out, okay, find out the adjacency matrix. And we go also with what is the adjacency list, or like, you know, these kind of things, right? So what is this adjacency matrix? Just, I have a question, so I just want to give you a rough idea, or like just tell you like what this adjacency matrix is, so that even if you don't know that, so here is the time where you can understand this, and then you can attempt that question. So a matrix with a rows and a columns. So in an adjacency matrix, it's just a matrix. It will have, you know, some m cross n, where m is number of rows and it will have number of columns, okay, which will be labeled according to the basically the nodes, right? So you will label them as such, and you also give them, you assign them the value, like you say 0, 1, 2, 3, 4 in an order, right? So that's what you give. So when do you give this entry as 1, and when do you give this entry as 0? So you see, you give this entry as 1 when there is an edge between the two vertices. Okay, so when there is an edge between the two vertices, then you assign a value 1, and if there is no edge between the two vertices, then you assign the value as 0, right? So this is simply how we do it in an adjacency matrix, what we do in an adjacency matrix. So it's just to give you a recall. Okay, so you see here you have a graph G. Now it has 5 vertices, you can see, right? So now you see that adjacency matrix for this graph G is something like this. So I just want to give you an idea here. You see this. So as I was telling you, so this is what your adjacency matrix look like, right? And you see here on the left hand side, this is basically rows and this is your columns, right? So what are this A, B, C, D? It's just the vertices which we have written, right? In an order like A, B, C, D, E. All right. So you see this, if there is an edge between A to A, so could you see if there is an edge between A to A? So there is no edge in itself, right? So that's assigned 0. Is there an edge between A to B? The answer is yes, there is an edge. So we give it a value 1. Is there an edge between A to C? Yes, there is again. So we give it as 1. Again, is there an edge between A to D? So yes, so we have given it as an 1. So this is how you give the entries, right? And do you give, so now again, A is paired with E, right? There is an edge between A and E, and therefore it has got an entry 1. Now you see that. Now you see that. Now again, you can check with the other. Now what about B? Now you see that B is paired with A, C, D, but it is not paired with E. So we can just look at entry D to E. Is it paired? It wasn't paired. So you see there is an entry 0. Likewise, you can fill all, right? And you obtain this nice matrix like this. So one thing you have to understand from this matrix is, now you see this diagonal entries, right? These diagonal entries are 0, right? So, and you see this, above this, there is a upper triangle. This upper triangle, and look at this, notice this lower triangle. The entries will be same. So it's basically a symmetric matrix, right? So adjacency matrix are symmetric matrix of what? For an undirected graphs. So that is also an important. It's not for, you cannot say it for a directed graph. So there are 2 types of, so this is for directed graphs. Sorry, this is for undirected graphs. So you see there is no directions given here, right? It's not directed. So a directed graph will have an adjacency matrix, which is a symmetric matrix, right? And you see this, you take this entry A, right? Now you see this, when you take the first row and you add these values, what do you get? when you add the first row, you get 4.
Degree of
So 0, 1 plus 1 plus 1
Four,
plus 1,
four.
which is 4. So you notice this. This is essentially a degree of this vertices A, right? Now you see this. What is the degree of this vertex A? You see there is 4. So you see, you notice the same thing here. Essentially, since this is a symmetric matrix, you can either add this or this, right? You get the same thing. You both of them gives you the basically the degree of that edge. Sorry, that vertex. All right. So this is one essential thing which you have to know. And notice one thing: this is an undirected graph. An undirected graph graph's adjacency metric is symmetric matrix. Okay, and when you add any rows or any columns, right, that gives you the vertices of that particular. Sorry, that gives you the degree of that vertices. All right. So this is one thing we have to understand. So now, based on this, we have a question: a matrix number of a non-zero entries in an adjacency. The maximum number of a non-zero entries in an adjacency matrix of a simple graph having 5 vertices can be. Now, what are we asking? Non-zero entries. So what do you mean by non-zero entries? Non-zero entry means the entry number 1. So what is the maximum number of ones that you can have in your adjacency matrix, right? So we are asking a maximum number, and how many vertices we have given you? 5, right? So quickly give this answer. Maybe you can take another 2 minutes. Think about it.
Done, sir.
Yeah, good. So just try solving this. So week 10 is essentially easy. It's just that some concepts which you have to know. Week 12, you will have more concepts. It's all about algorithms.
Actually,
Again,
we
those
can
are,
use
12 is revision, right?
that to CT computational.
yeah, and you also learned it in CT. So this is kind of, it's like relaxed week for you, all of you, after calculus. And all that you have to know, it's just the concept. If you know the concept, you can solve any problem here. You will not have a bigger problems what you can get it in the calculus or in some other functions which you would have noticed it. There you just not need to know just the concept, but also the problem solving skills. Here it's very straightforward. Just know the definition, solve some questions. There is a standard questions which will be asked, so it's very scoring, right? And since this was never asked in your any of the quizzes, so it will have more weightage. So that is also there. So, all right. End term, all these things we'll discuss at the end. We'll keep that at the end. Okay.
Okay.
We can discuss all that. Yeah.
Sir, did you mean week 11?
No, graph theory as whole.
No,
I mean,
you're talking about algorithms, right?
algorithms. Yes. That you have it in week 11.
Okay.
Yeah. Yes. So now let's see what are the popular response, and those who want to give the answer for this can raise your hand. So the popular answer is option D, which is 20, but most of you have also given answer as A. So okay, let's see. So I can see 2 of you have raised your hand. We can ask. So Shreya have already asked. So maybe Abdullah, you can answer this time.
It is 20 because we have 5 vertices, and the number of maximum for the 5 vertices, maximum edges can be n-1.
Right.
So 5 into 4, 20.
Right.
20 would be maximum.
Right. So perfectly right. That's very straightforward. So nice. Good, Abdullah. So you have, so this is one small questions which we asked. So it's just that, right? So here you have 5 vertices. So you have A, B, C, D, E. And if you have an edges, between any pair of the vertices, then we will have a maximum non-zero entries in an adjacency matrix, right? So what do you have to make sure that all of them are paired with all of them? So basically a complete graph, right? So if that's the case, then what? Some graph like this, right? So you see all of them will have degree n-1, right? So A, if you look at A, so what is the degree it has? 4. Look at B, it has degree 4. Again, C, E, and D will have 4 degrees, right? So that's the condition. So how do you actually make sure this? So you see this, one way of telling is maybe just we have drawn this. Now you can see the adjacency matrix for this. This is what you look like. So you'll just have diagonal elements being 0, except that everything is 1, right? So a complete graph will have how many ones entry? So it will have n into n-1 essentially. So you see this. So it's just the same thing. It's explained here. It's just that, you know, the number of entries will be 1 plus. So it's basically, in other words, you can actually say that one way is knowing is this solution, what is given. Another thing, what you can see is, since each vertex has 4 degrees, right? And how many vertices we have? 5. So it's 5 times 4. So that's 20. What Abdullah told was very straightforward. So we can follow that. All right. So no doubts over here, right?
So we can explain it in another way.
Yes, please go ahead, Shreya.
So
Is it Shreya or some other?
Yes,
person?
Shreya.
Okay, Shreya. Yes.
So we can also say that we can't map any vertex to itself.
Right.
So because there are 5 vertices, maximum is 5 times 5, but you have to minus 5 because no vertex can pair with itself.
Okay. It's essentially the same thing, but yes, what you are telling is in your way of understanding. That is perfectly okay.
Okay.
Yeah. All right. Okay, so now let's go with some BFS trees. All right. So here, I'll tell you what are the typical 2 type of questions which is asked. We'll give you a graph, and then we'll ask you to find the BFS tree. Okay. So, or we might tell you, okay, this is you have to let it be the sequence in an ascending order or in an alphabetical order. Then tell us what is the sequence of that BFS tree. Now, these are the popular questions. Other thing is, maybe we'll give you a BFS tree, and then we'll ask you to find out which are the possible edges that original graphs can have. Okay, so these are the only 2 problems we can ask you. Or what else we can do with, since this graph is given, we might ask you to find out what is its adjacency matrix and all that. Okay, so but essentially when it is about BFS tree, it's the 2 things, that's all. We'll give you a tree, we'll give you a graph, and then we ask you, okay, find out BFS tree. Or we'll give you a BFS tree, and then we ask you to tell us what are the possible edges that this tree could have in the original graph. Okay, so you see, if this is a BFS tree, right, and we always tell you what is the node vertex, so we tell you the root vertex basically. So here we are telling you, originally, you see, if you have a BFS tree and we are saying your starting node is A here, right? So when we start building this BFS tree, so, you know, I'll tell you how is this happening, but for time being, you can just understand this. You can stay with me at the end. I'll tell you those who have problem, like how to draw the BFS tree. Maybe I can help you out at the end of the session, how to draw the BFS tree from the graph. Okay. So as of now, just keep it in your mind, like this is how it's done. Now you see that from A, so you see, you get, this is your tree. This is your graph, and you obtain the tree something like this. All right. So now there are 2 things which you have to understand from this. Okay. So now you see this graph and this BFS tree. See, both the vertices at the level I in the tree may have connected by an edge in the original undirected graph. So you see this, basically A to B and A to F. You see that there is an edge connecting B and F, but in your tree you don't have it, right? And you see here, I'll tell you, this is level 1, and this, consider this as level 0, this is level 1, level 2, and this is level 3. Okay. So now you have 3 levels. So what do I mean is, this is just draw a horizontal line at A, call that as a level 0, and draw a horizontal line at BF and say that as a level 1, and then similarly draw a horizontal line at EC and say that as a level 2, and DG as a level 3. Okay, so what I want to tell you here is you can have, so basically on the same level you can have an edge in your original graph. So if I tell you this is your tree, okay, this is your BFS tree, so on the same level, so you can draw an, so basically you may have an edge in the same level in the original graph, and also a level above, that is I, you can have an edge between the level I and I plus 1. So basically you can have an edge between level 0 and 1, but you may not have, but you will never have edge between level 0 and level 2. So it's essentially you will never have basically edge in level I plus 2. So maybe I have confused you, I guess. Is it? Any of you got confused?
No, sir. No, sir.
No?
Easy.
Easy? So all that you have to keep it in your mind is you can have an edge between, you can have the edge in your original graph, which is this, okay? You can have an edge between B and F. So B and F is on the same level, right? And also you can have an edge between what? Between these two, that is E and D. These are at two different levels. So this is level 2, sorry, level 1, sorry, level 2 and level 3. And also you can have, you know, you can have an edges between two different branches as well, but you have to just obey the label, that's all. Okay, I hope this is okay.
Sir,
or you need some more explanation?
Sir, in this graph,
I guess you know them. Sorry, yes, please go ahead.
In this graph, EC and G in the same level. So why we can't go A to B, B to E, E to C, and
okay. EC, right? EC, right? Okay, so if you see here E and C, yeah, you can see EC, you can definitely have an edge here. So now if this is your BFS tree, you can definitely have an edge EC. Now, okay, you are asking how did this graph came into picture, right?
Yes.
Okay, so for that you'll have to wait. All right. Okay, we can draw that graph later on, so don't worry about it. But for time being, just understand that in your original graph you can have edges on the same level, and in the level I plus 1, okay, but not I plus 2. All right. So what about DFS tree? So in DFS tree, for an undirected graph, you can only have edges in the same branch. Now, I don't know, maybe I just wanted to create two slides, but here the answer is already there, so you can just tell it. So why does this happen? Because if you see, if there is an edge between the two vertices of a different branches, then the neighbors of that vertex must be visited in the order to remove from the stack, right? So that is what we do, right? So you can have an edges on the same tree, okay, but you can on the same branches, but you cannot have the cross edge branches. You cannot have an edge between the cross edge branches, okay? So in your DFS tree, so this is one thing you have to understand. That's all. So you don't have this concept of level I and and I plus 1 and all that, right? Here you have to just obey that. If it is the same branch, then you can definitely have an edge in that branch. All right. So maybe I'll take up some questions at the end and give you more explanation while I'm writing it on the board. So then you will have better clarity. If you did not understood, that's okay. We can discuss at the end. All right. So, but I think this is very straightforward. It is something told in the lecture and also in the previous live session. So that's very straightforward. All right. So based on this.
Excuse me, sir.
Yes. Or essentially, when we are doing some more problems.
So, can you move to the
previous slide? Okay.
Yeah. This one, sir. Instead of for the B, instead of writing the E this side, can we change that E to the C, C to the E? It would be same, right?
Okay, you're talking about drawing this tree, right? So you are going from A, then you have B and F, Okay, and from F you cannot go
Yeah.
anywhere, but
So
from B you
B,
can go to,
we have E and C.
right. So
Yeah.
you
So
can go to
can
E
I
and
exchange
C.
that? I mean, writing the C part to the E and E to the C.
Okay, so essentially you want to do like that, right? So, but again, you will land up going there itself, right? So because you see, when B is your, when you visit B, right, then you explore this C and E. So let's say you are telling that I want to explore E first, right? That's what you mean.
No, sir, because accordingly, I mean, first comes the lower number. So A, then B and F. Among B and F, I have written the B first, then the F simultaneously. But the preference is the beginning with the smallest one. This is my understanding. So
Okay.
from the
Okay.
B, we have C and E. So C, writing the C on this side, I mean, on the left side, and E on the right side. Again, from the left hand, we have C, right? So C will be again getting sub-branched. So is that okay?
Yes.
Same,
Yes. 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 Yes.
same
Yes.
graph?
Yes.
It will be same. It will be
It
same
will be the
actually.
same. Yes.
Thank
Yes.
you.
Yes. Yes. Yeah.
Okay, thank you, sir.
Yeah. Good. All right. So now we have a question for you based on those things. So, suppose we have been given you, we have obtained the following BFS tree, which is rooted at node A, okay, for an undirected graph with vertices A, B, C, D up to some J, I guess, or some big number. Which of the following cannot be the possible edge in the original graph? So if you did not understood what I was explaining you there, you will understand it here if you could not answer this. So let's see how many of you can give this response. So maybe you can take another 2 minutes to give this answer. I'll mute all. Do any of you need more time?
No, sir. It's done.
They're done. They're done.
Done, right?
sir.
Okay, so anybody can explain this? Can any of you raise your hand? Okay, Shreya. Okay, Shreya. Yes, please go ahead.
That's
From
not me. It's the
uh,
other chair.
I'm a different Shreya.
Okay, Shreya Par. Okay.
So we know that a vertex from the level I cannot form an edge with another vertex from level I plus 2.
Right.
So here E is in level 3 and I is from level 5. So that's why option C will be correct.
Okay. So So basically, can you have an edge in your original graph with I plus 3? Yeah, I'll mute all. Then you can unmute yourself. Shreya, can you answer this?
No, I'm not sure.
Okay. So you can only have edges on the same level or the level I plus 1. That's all.
Okay. Yes,
Not
yes.
more
So
than that.
I remembered. For it can happen for I plus 2 or more.
It cannot happen for I plus 2 and it cannot happen for I plus 3 and more. Okay, like that.
Yes, yes.
Yeah, but maximum I plus 1 or same level.
Yes.
So let's see what are the popular answers. Oh, 8 of you have given B as also the answers. So I hope those who gave incorrect answers, they understood now. You see here, so maybe we can just explain this. So thanks, Rhea. All right, so let's see so maybe you can just go through these slides. I just want to explain you here what the solution is given. You can go through that later on. But you see here, B and K. So let's spot where this B and K are. Here, B and K. So you see this is at level. So A is at level 0. This is at level 1. So let's see how many levels do we have. This is level 1, level 2, level 3. Then we have level 4. So we have maximum 4 levels, right? So now you see that B is in level 1 and K is in level 2. So it's just one level above. So certainly you can have an edge between these two in your original graph, right? What about M and N? So let's see M and N. So now this is one level above, that's all right. So you can certainly have an edge between them. What about E and I? So now you see this E is at level 2 and I is at level 4. So it's like I plus 2 where you cannot have an edge. So this is wrong, incorrect. So basically you have been asked to find out which among them is incorrect. So this is C something you have to select. What about D? Now you look at D. D is E comma H. So E and H. So you can certainly again have here because this is at level 2 and H is at level 3. So it's just one level above. All right. So it's the same thing written here. It was much easier to explain there. So you can just go through this. If you don't get it, it's self-explanatory. You can just read this, you will understand. All right. So that's about that. Now let's go with one question on. So you don't have any doubt there? Any of you have any doubt?
Sir.
Yes.
Sir, how to convert this graphs into original graphs, sir? I couldn't get it.
How to convert this?
Yes, sir. Undirected graphs into original graphs. BFS and DFS into original graphs, sir.
Okay, so maybe we'll take this at the end. Okay, so don't worry about this. So I have some questions.
Hello, sir.
Yes.
Sir, in this, can H and D have an edge? They will also not have an edge.
H and D, right? No, even they will not have, because see, there are two levels different.
Yes, sir.
Yeah.
Simply that H can have edge with E, F, K, N, but not with D, C, B.
Yeah.
One level above.
But it can also have edge with H can also have edge with G, M, L, right? Because they are on the same level.
Oh yes. That
right?
I got.
Understood,
Yes.
right? Yeah.
Okay.
So any other doubt here? No doubt. Okay. So this is one type of problem. See, what we have given here is we have given you a tree and then we are asking you to find out, okay, which can be a possible edge in the original graph. Another thing is we just simply give you the graph and then we ask you to find out the BFS tree or DFS tree, right? So that is the another popular type of questions. Okay. So these are only two type of problems you can expect, not more than that. All right. So now let's.
Sir, sorry.
Yes,
sorry to interrupt. Sir, actually the thing is the ones who don't have that online degree, ID, that IIT ID, only they are not able to join. Like the ones who are in the January 2022 batch, so they are not able to join specifically. So if you see here on joinpd.com also, there are like 58 students there. But
yeah, that's what even I was wondering about. I was thought like,
Zoom 35 are there only.
I see.
Yeah. So that is the problem faced by only that January batch.
Maybe I can just ping them once. All right. I can just tell them once that this is the problem. So they don't have ID, so they could not join this session. All right. So I'll just ping them once. Yeah. All right. So so maybe I can just do that in a minute when I'm giving you a time. So vertex coloring of a graph. So now here, find the minimum number of colors required to color all the vertices vertices of the given graph such that no two adjacent colors have the same no two vertices have the same color. So you know what that vertex coloring is, right? So this is a big graph given to you. Now you have to tell me how many colors you can have, right? So this is not a question. So it's just to explain you. So you see this, how does the filling, so we'll do that filling color with red. Okay, so that is something, it is shown here. So you see this, when I select this as, when I select A, give it a red color, I cannot give same color to D, right? So let's say here we have just two colors, that is red and white. Okay, so you see if there is an edge between any two vertices, then they will not have the same color, right? It's very simple. Now you see that A and C, they are connected, right? And they share an edge, right? So therefore they cannot have the same color, they will have a different color, right? And similarly A and D, they does not have the they share an edge, so they will not have the same color, right? So therefore A is given a red color, C should be given a different color, which is given white, and D is also given a different color than red, which is something given as white. Okay, so this is, you can see similarly E and F, sorry, D and F. So here is a mistake, I guess. D and F, they are connected, right? And we have given a same color. Have you noticed it?
Yes, sir. It is the same for B and P also.
Right. So
Yeah.
do you think this is correct or incorrect?
Incorrect. It should be incorrect.
Right. Because you see, we cannot give the same color for them, right? Therefore, we should do something else, right? We should change the color there. So maybe I can just take you to the end, the one which we have it here. Now you will not have any doubt, right? So now you see this, this vertex A has given red, has been given A as the red color, C has been given green color, D has been given D color, because they are not sharing any edge, so we can give the same color to them. Similarly, all we have to do is we have to choose very minimum number of colors, right? And we have to optimize with that minimum coloring, right? So that is what we do here. So now you see this, E can also be given same, A and E can be given same color again, right? So certainly that is definitely, I can give that. But you see F cannot be given red color again, and it cannot be given green color also. Why? Because F shares edge with D and E, so therefore I cannot give them the same color. I cannot give them red and I cannot give them the green color, right? Therefore we have to select some another color. So maybe we have taken it as an yellow, right? Similarly, you see G should be given a different color other than green and yellow, right? So which is that we should use? We should use the one which we are using it already, because we have to minimize the number of colors. We have to choose a minimum number of colors, right? So therefore we choose it red again, because these are the three colors we are playing around. Similarly, likewise, you will find only three colors will be required for vertex coloring of this graph. All right. So all you have to keep it in your mind is, when you are doing this coloring problem, you have to choose the minimum number of colors and make sure that two vertices, if they are sharing the edge, they should not have the same color. That's all. Based on this, you have a question. So here in this particular,
we can have multiple answers.
Multiple colors you can have, but the cardinality of that colors will be 3. You can have any color.
Cardinality would be same, but
yeah.
Okay, sir. I mean, color pattern would maybe different.
Of course, you can have it different, yeah. But cardinality should be same. Yeah. All right. So based on this, we have given question number 3. Yeah, you're welcome. So now based on this, there's a question. Now here a company manufactures 10 chemicals. Certain pairs of these chemicals are incompatible and would cause an explosion if brought into contact with each other. Okay, so we have to make sure that they are on the same different compartments, right? If they are together, there is an explosion, right? So we have to separate them. So basically this should give you a hint that this is something like a coloring problem, right? So below graph shows, I have not shown you the graph yet. I'll show you that. Below graph shows the incompatibility of the chemicals. Each vertex represents the chemical, and each edge between the pair of the chemical represents that those two chemicals are incompatible. So if there is an edge between the two vertices, it indicates that these two vertices are incompatible. All right. So as a precautionary measure, the company wishes to partition the warehouse into the compartments and store incompatible chemicals in different compartments. All right. So if that's the case, so here this is what it represents. So you see that your chemicals are represented with the vertices and incompatibility represented by these edges, right? So F and G, if they are stored together, that means if they have been given a same color, so they are going to explode. So we have to make sure that they are put in a different compartment. So basically, they should be given a different color. So it's a coloring problem. Based on this, just take a 2 minute and try to solve this question. And till then, I'll ping the admin team that this is the issue the other students are facing. So maybe the qualified students can hear me here on this portal. So I have just escalated this thing to them. So let's see if they can allow you at this point of time or not.
Sir, one of the student is asking, like, uh, whether if this type of problem comes in the exam, we have to like draw the entire graph on paper, or like we can just directly see on the screen and solve it.
It is better to draw the graph on the paper and then give that coloring.
Okay, okay, yeah.
Right? Otherwise, how can you do it, right?
So, sir, in the exam,
Okay,
we need 4 or 5 pens, different color.
You can use the numbers.
You can use different symbols, no? Like
Symbols or the numbers. Numbers is also the best. You can give the number 1 for color red, number 2 for yellow, green, or whatever. Maximum color you can have is 4.
Maximum will be 4.
Yeah, that's all.
So 4 different symbols or 4
even
numbers.
that is okay. Even that is okay. So do you need some more time?
No, sir. We can.
You can do
No,
it,
sir,
right?
it's done.
It's done already. Do any of you still need time? No, right? I don't know about qualified students.
No, sir, it is done.
Yeah.
Sir.
I have raised this issue. So let's see how soon we get the response. All right, so let's move. What are the popular answer for this? 2, 4, 3, 7. Oh, nice. So, like this is really, you should definitely keep it in your mind that maximum color for a planar graph, you will not have, like not more than 4 colors will be allowed, because that's something even prof has told, and there's proof for that as well. So interestingly, even after this, I have seen in previous term, like some of a vertex coloring problem was there, and like they were some students giving answer as 10, 12, this kind of answer, which was really strange, but not much maximum, but that was strange to see. All right, so good. So still unable to join answer. So, okay, yeah, I get it. Okay, so let's see how is this done, right? So it's very straightforward. So I can just simply go with the main color thing, and then we can just see. All right, so this is our step 5. So that's done step by step. We can simply just go it in the same way. So how many 4 compartments are needed, right? So you can see, as all of you got this answer, but some of you are giving answer as 6 and 7, and you have to minimize the colors. You are not free to use multiple colors, right? You have to minimize the colors. That is also a problem. You might obey the thing, but you might land up taking different colors. That is something you shouldn't do. You should minimize the number of colors. All right, so that is something you have to keep it in your mind. So all right, so now you can see this following the same principle, that no 2 vertices sharing an edge will have the same color, right? Based on this, and you also have to make sure that you have to minimize the number of so this is what this is an optimization problem. So you have to make sure that you are minimizing the number of colors, right? So now how you do this? So obeying these 2 things, you will get this this 4 colors. So you see this, none of these edges share the same colors. Now you see this F and J, they share an edge, but they are with different colors. Now similarly, B and F, they are of different colors. We could have also given this as a green instead of this blue. We could have given it as a green as well. Even that was allowed, because you see that this J and B is not sharing a color, so we could give it the same color. Sorry, we since they are not sharing the edge, so we could give the same color, right? That's what. So you see, even same here, same goes with this. So anyhow, that anyways it's not merging, so it's based on which point you choose, and then actually go around with that colors and you choose that. So that's okay. You will have different patterns, definitely. This is one pattern you get, that's all. So do you have any doubt in this particular question?
Sir, is it planar? I mean, the lines are crossing, so can we still call it planar?
This is not, basically, because since for this particular thing it's happening that 4 color was sufficing the need, so that's okay. So like you can still draw this, but again this will have some kind of crossing. So I don't think so this is a planar graph. So certainly you can have different colors.
Excuse me, sir.
Yes.
So the condition is that only for the
planar graph, maximum 4 color will.
We have no such condition, right?
Yeah, no such conditions. Yes.
Okay, sir. Thank you.
Okay.
Thank you, sir.
Yeah, good. Yes. Any other doubt? Yes.
Sir, I did the B also green, so that's why my answer came as 5. I don't know.
Okay, so let's try that with the green, and then see if you gave it this as a green, then you should have chosen this as some different color. So maybe you should have gone with so can we try? So let's do with your thing what you have done.
I think we could just interchange the C and E colors, no, in that case.
Yeah, even that is right. just check that. Can you do that?
Yeah.
You just have to change that.
We can interchange C and E. Yeah.
Check that.
Okay, sir.
Yeah, just check that, Shreya once. I think you should get it. Just obey those conditions. That's all. You will get it. All right. So what vertex coloring sum based on when you're adding some edges, right? So now we saw that coloring. We saw that a colored graph in our previous slides, right? So now the question is, we can still add some edges in the graph so that the coloring of the graph does not change. All right. So can we do that? Now you see this. This is something we did it in the very first when I was explaining you this when we were on this coloring slides. So you can see this graph here. So let's see what else we can do. So can we do this? You see that A and F, can we have an edge between them? The answer is yes, right? Because I'm not violating this condition, right? I'm not violating this condition because A and F initially they were not sharing an edge, but they have different colors. So certainly I can give them an edge, right? So you're adding an edges. So there is some additional thing we are doing. That's all. This is nothing much. It's just a practice. So you see again, C and F, they were not connected, but they are of different colors. So we can connect them, right? That is something we can do, right? Similarly, we can do with BF, right? Sorry, HF. Where else we can do? Can anybody point somewhere else?
G and P.
Yes, G and P.
F and P.
F and P. F and P. Yes. So you can have all these. There are so many things which you can do. All right. So what do you mean by planar graphs? So again, a hint is given already. So you can just tell it. A planar, a graph is a planar. So I'm just reading the same hint. If there is a way to draw the graph so that no edges are intersecting each other except at vertices. So this is only it means, right? So this is what it means. So you can have an edge between A and D. You can have an edge between A and F. So when you have this edge AE and AF, can you have an edge between CD connecting from here?
No,
Yes,
sir.
Abdullah?
No,
right? But you can draw it something like this. From outside, you can draw them. From outside, you can draw them. You can draw like this, right? You can see my cursor, right? That is allowed.
Yes, sir.
But they are not intersecting. All you have to make sure that they are not intersecting each other. That's the only thing you have to obey, right? Similarly, you can have edge between C and F. So we drew it internally, so that was okay. Then, so how many edges that you can have? Okay, so let's not go with this. Maybe I have a problem there. We can do that. So you see, these are the two things which you can do. You can do with AE. You can join this AF. You can join this CD. You can do this ED. Can you do any more? Can you do this CF? Can you do CF?
Will overlap with D.
Overlapping, yeah.
Overlapping, or they will intersect. You see, it has to intersect this F, and then it has to, this red line, and then it has to go to F, right? So that will happen. So I have to make sure that they are not intersecting, right? So I can have these many edges. So how many edges do we have here? So okay. So what is the degree for this? Could you tell me? Oh, some interesting thing. Can you figure it out? Maybe I don't think so. You can talk more interesting thing with the degrees here, so we can just avoid that. All right. So let's go with this question 4. So that was very straightforward to tell you.
Sir, how many edges were there in the earlier graph?
Okay, so here earlier you had it 1, 2, 3, 4, 5. Then how many possibly? We drew 4 more. We had it 9. Yeah.
9. Okay.
Yeah. All right. So based on this, you have a question. So you just have to do the same thing. An incomplete undirected graph is shown here, and the numbering on each vertex denotes the coloring of the graph. So So you see that one represents one particular color. So it can be any color, red or like any color. So one represents one particular color. Two represents, it denotes another color, right? Let's say a color 2, and 3 denotes color 3. Now we have to find the number of maximum edges that can be added to the given graph such that the coloring is retained and the graph is planar. So there are two things that you have to make sure, right? You have to make sure the planarity of the graph is not violated. So it has to be a planar, and also you are not violating this. You have to retain the colors. Okay. So now let's see how many of you can answer this. So two things you have to keep it in mind, that it has to be planar and the coloring is retained. So you're adding edges such that the coloring is retained and the graph is planar. So how do you do this basically? So when you have this, you first maximize the inner edges. So that you can see in the hint as well. It's written that we have to maximize the inner edges. So you first draw the inner edges, then draw the outer edges. Okay. So take time. Take your time to solve this. Maybe we can give you 3 minutes. So to as qualifier students are not able to join, so I just spoke to the team. They're like, we need to end the session and then all of you can rejoin this session again. Is that okay? It'll just take a minute or a two so that even they can join here. All right.
Okay.
So all of us
Same.
can leave this
Sure.
and
we are same?
rejoin here.
Okay, sir.
Yeah, same link, same link. Okay.
Okay, sir.
Leave from the Zoom.
So essentially, okay, so now it's being live streamed, so they can see me. So it's, I don't think so. Like for today's session, the qualified students will be able to join. They tried fixing it, but it is not happening from their end. So we can meet on the other session. But yeah, be active on YouTube and you can convey your messages. Maybe even I'll come to YouTube and see your queries there. So that is we can do. So let's wait for the other people to join. So till then you can attempt this question. All right.
Sir, do this type of questions can be expected in the final quiz?
Final
semester exam?
No. You can just think this as some kind of practice problems. But of course not this time, but these are some simple questions, but not in the end term. I don't think so. We give some end term question like this.
Okay. Thank you.
Yeah. So I hope like those who are there on this Zoom link, they have solved this already, or you need some more time.
Yes,
solved,
sir. We are done.
Solved, sir. It's solved.
Solved, right? Okay. So I could see like 31 of you have given response. So let's move ahead then, right? Or let the others also join. Maybe I can just wait for 2 minutes for them, and then we can start. Okay. So what are the popular responses? So popular responses are 5. Okay, so since this is just a response, so a diverse answer. So 6, 4. What is this? Affirmation, thank you. Answer is 9. Okay. Is there any organized way to solve the coloring problem? So it's just that principal definition. That's all. So that's the only thing you have to obey here. So it's just that you have to make sure that no two adjacent vertices. Adjacent vertices means they are connected with an edges. No two vertices connected with an edges should share the same color. That's all. That's the only thing you have to understand. Algorithm there is, but I think that's very complex. So we will not be dealing with that here. So answer, we are still logged out, I know. So answer is 9, 5, 8, 7, 7, 7, 8. Okay, so very diverse answer. So 7, 8, 9, and many other answers. So let's see how to do this problem. So you can see, do any of you want to explain this? Maybe any of you can raise your hand here. Maybe Sonal Pandey. Are you here, Sonal? Abdullah, can you want to explain this? Okay. All right. Okay, Abdullah, please go ahead. Yes.
Actually, we have to start with the number of edges that can be drawn newly inside the graph. I mean, without going from outside. So direct lines inside. So I have started with 1, and I have tested. I mean, where can I go with the 1? Like different numbers can be patched up. So I have patched up 3 with the 2.
3 with
and
2.
3 with the 1. I mean, I have 2 with the 3 and 2 with the 1.
Okay, so maybe I can just show that graph. Just give me
yes.
I can just show you that. Okay, so these are the popular thing. Yes. So the inner edges, Abdullah, as you are telling, you have given this as 2, 3. Abdullah, are you here?
I got it wrong. So
you got it wrong, but it's okay. You can attempt trying. You can tell it here still. So maybe
first thing, joining the inner edges. Thereafter, while joining the outer edges, I have to keep in mind that I have to add the nearest one first, then the farther one next. I mean, this is the thing I have to do.
Okay, great. That's okay. That's okay. But you see, these are the possible ways. So as it was told, that's okay, Abdullah. You tried it, right? So anyways, the answer is 9, and I have seen like some of you have given answer as 9, not most of you. It's okay. This was just a practice problem because this involved a coloring concept, and also when such question is there, we checked your 2 knowledge. One is that you know coloring, that means you are obeying the definition of coloring, and also you know the concept of planar graphs, right? So these 2 concepts are tested here. So of course this is not a very simple graph. It's 2 graphs merged, right? So it's not very easy. That's okay. So let's see this. Let's learn it, how to do this kind of problem. So you see this, you can have an edge between 3 and 2. So how many inner edges that we can have? So as Abdullah was telling, you can have it with 3, 2 and 3, 1. So you can also have edges with, but you cannot have any more edges in this first pentagon, right? But you see in the second pentagon, again, the similar thing can be done. But now where all you can have edges? Now you can have edges between this 2, 3. We can have edges between this 2 and 1. We can have edges between 2 and 3, right? Can you have edge between 2 and 2? No, that is something you cannot do because they are of same color, right? So you cannot do that. So that is not allowed. So that is gone. Then now let's check with 1. Now from 1 I cannot go to 3 because we already share an edge, right? So here it's already shares an edge, so you cannot go there. So 1 to 2, yes, you can go. So you have this connecting here. And then you can go to 1, 2, 3. Yes, that is also allowed. So you can see here, this is something drawn here as well. Likewise, what else you can do? Can you have any more edges between this 1 and 2? Can you? So you just did it here. I mean, we just did it here. So now can you have this edge between 2 and 3? So that is something drawn it innerly. Can you do any more edges here? No. So it's just a simple practice. Just two things we have to understand: planarity and the coloring concept. That's all. And we get the answer. So we have to be very cautious here. Rather, I would say you should have to be very cautious while solving this problem, because we tend to lose some of the edges. We might not give the right number of edges. So we have to just like we just have to give a practice for this and be very cautious while solving these kind of problems. All right. So do you have any more doubt here? No, right? It's just that two definitions. You have to keep it in your mind while solving this and just give a practice. That's all. And be cautious. That's it. Okay. So I hope you don't have any doubt.
Okay, sir.
All right. So now let's go with something DAG. I think in the previous live session, it wasn't discussed this concept. So we can just take up here. And also, like, of course, it's very well explained in the lecture. So I don't even feel there is a need for this here, but just to bring everyone on the same page, like who haven't seen it or something. So you see some facts about DAG. So what are DAGs? DAGs are directed acyclic graphs. Okay. So basically, they does not have any cycle. So you should not, even a subgraph should not have any cycle. That is what it means. Okay. So every DAG have a vertex within degree 0. Okay. So every DAG has a vertex within degree 0. So that is something, this is another fact that you have to keep it in your mind. And every DAG has a vertex without degree 0. Okay. So what else do we do with this DAG? Why are we talking even about this DAG? So there are two types of problem mainly that you would see in this source lecture. It is more about topological sorting and longest path. So topological sorting is there in your week 10, but as soon as you start your week 11, it will be starting with longest path, which is the concept of DAG itself. All right. So do not segregate these 2 weeks as two different weeks. It's basically 1 week itself, but since this week is too big, so it's bifurcated into 2. Okay. So you treat this as a continuous week and then you learn them. Okay. So over here, we will be first learning what is DAG, and then we'll be doing this topological sorting. Okay. So let me see if we have, okay. So we are directly going to topological sorting, but I just want to give you some idea about DAG. Okay. Just to understand how does this DAG look like. Okay. So maybe I can just draw something and just check how much we can answer this, right? So let's see this. Maybe I can just draw some graphs and then I ask you whether this is DAG or not, right? So the name itself says, what is DAG? Directed acyclic graph. So two things you have to understand. There are two keywords: directed. So there is the direction in your graph, and acyclic. So it has to be acyclic, right? So now these are the two things which you have to keep it in your mind, right? So let's see how many of you can give this answer. Maybe I can just draw some 1-2 graphs and then check your knowledge, like how many of you can answer this. All right. So now you see this. Then we can go to that slide, because the next slide is just about topological sorting and nothing much about DAG. Okay. So now let's say this is A. You have to figure out which among them is DAG. Okay. So which among the following is DAG? Okay, so that is something you'll have to tell me. which among the following is DAG? Okay. So first A, then you have it, let's say B, let's say then you have it some C, let's say we have D. All right. Let's say this is also like this. This goes like this, like this. Okay. So let's call this as, maybe we can call this as G1. Let's call this as G1. I can draw another A, B, C. Maybe I can say this as D. If this in this direction, this in this direction. Okay. G1, G2, G. Which among the following is? Okay, I'll mute all. I'll mute all. So which among the following is DAG?
G1.
G1.
G1 is DAG?
Yes.
Okay,
No, G1 is forming cycles, sir. It's not DAG, I think.
G1 is DAG.
G1 is DAG.
have no cycles.
G2
G1.
not a DAG.
Do we have
no
any more
cycles.
DAGs?
The G3.
G3 is DAG. No,
No.
it's not a DAG. I'll explain you why it is not a DAG. So only G1 is DAG. Okay. Why? Because you see there is no cycle here. So first of all, there is a direction in this graph. Right? Okay, I'll mute it all again. So you see there is a direction in this graph, right? All of them are directed graphs. And now all I have to make sure is it is acyclic. So can you see where all you can see a cycle formation? Is there a cycle in this ABC? No. So is there any cycle in ACD? There is no cycle again here. Now, is there a cycle in ABCD? No, again, there is no cycle here. So basically, this is a cyclic graph, right? So this is a DAG. This graph is a DAG. Okay. Now you see, what about G2? Is there a cycle here?
Yes.
And also this complete thing, right? This complete thing, isn't it? B, C, D, B, A, C. It's again. So even if you had even if you had a subgraph, basically a sub part of it forming a cycle, it is a cyclic graph. It's not a acyclic at that point of time. Okay. So this is not a DAG because this is cyclic. It's not acyclic, right? So this is not DAG. What about this? So this can also be written in this way. A, B, it's right. It can be written in this way.
Cyclic.
Right. So this is also cyclic. Right. So this is also not a DAG. Right. So I just have one DAG.
Non-cyclic and acyclic are same or not?
Non-cyclic.
Yes.
Okay. So I really need to know what is non-cyclic. Non-cyclic. It's all you have to keep it in your mind is something which is there are just two concepts: cycle or acycle. Okay. That's all.
Okay.
Yeah.
Okay.
Yeah. So these are the thing. This is just about DAG. That is something I just wanted to tell you. So this is DAG. So now what we can do with the DAG? So what are the applications of DAG? So one is topological sorting, and the other thing is finding the longest path. So that is the two things that we do. All right. So some facts about DAGs. That is something we have seen. So now let's go with something what is being discussed in week 10. That is something called topological sorting. So how do we do this? So what do you do when you're doing a topological sorting is you write down the in degrees of the vertices in the DAG. Okay. Then you find out the vertex U from the DAG that has in degree 0. And then you add the vertex U to the topological sequence. So it's basically a sequence of vertices. Okay. So that is something you have to understand. So topological sequence is nothing but a sequence of vertices just written in order. Okay, so what do you do then? Then you remove u from the DAG and update the in degrees of each of the remaining vertices, and then you repeat the process from step 2 till the last vertex is added to the topological sequence. All right, so this is in a trivial way, I mean in a nutshell, this is all a DAG. This is all about DAG. Okay, so let's go to the next slide. So next slide tells you about the question itself, but before going to question, I want you to answer me, since this was a DAG. Okay, now you notice one thing. I'll just remove the other part from here. Now notice one thing here. Just tell me what is the in degrees for each of these vertices. So as the first step, it tells you that you have to find out the number of in degrees. So what is in degree of A?
So for A, in degree is 0.
Okay.
B is
have
1.
1. C has 2.
Okay.
B2.
And D has 2.
D is 2. Okay. So now the next step is where D is 2, right? Okay. Now can you tell me what about the out degrees?
A has 3.
A 3.
A has 3.
B 1.
A has 3 out degrees. B has 1, right? C has
1.
Out degree
1.
And D has
0.
So we were telling you in that particular slides that in a DAG you will have at least one vertex with in degree 0 and at least one with out degree 0, right? So something you can see, you can notice here as well, right? So that is why it is a fact, right? So now how do you do? Next part was the procedure, right? So whichever the vertex has got an 0 in degree, you remove them first. Now you are finding a topological sequence, right? So you are doing what? Topological sequence. So topological sequence is just the sequences of a vertices written in an order. All right. So now what was the first step? That you have to remove this first vertex, right? So when you remove you will have to remove that vertex which has got in degree 0, right? So when you remove that A, so that comes here in your sequence, right? So when you're removing this A, so this all thing goes out, right? Even this connecting edges goes out. So then I'll be left with what? B, C, maybe I'll use the same color. So what I'll be left with? I'll be left with B. So I'll be left with B, C, and then D. Now you tell me what is in degree of B. So I'll just talk about in degrees. Can you tell me what is in degree of B? 0. What about C? What about D? 1. In degree. We are talking about in degree. So now you see this. Once I remove a vertex with in degree 0, the resultant graph is again a DAG, right? This is again a DAG, right?
Yes, sir.
So this is another fact. From a DAG, if you remove a vertices which has got an in degree 0, the resultant graph is again a DAG. This is another fact that you have to understand. All right, so I'll mute all again. So now what? Again, I'll update my sequence, topological sequence. So what is the next thing that I have to do? So again, so now I'll just remove this B. Now I'll remove this B again, and then I'll be left with what? So maybe I can just write down B here.
C and D.
Then I'll be left with C and D. So
C and
what is
D.
there in degree? In degree 0 and 1. Is
0,
this
1.
again DAG? This is again a DAG? Yes,
Yes.
that is again a DAG. So now I'll have C. Then I'll left with D. The last one which is left, it's just written like that.
Yes.
So what is the sequence? Sorry, C and D, right?
Yes.
So this is what the topological sequence is. Okay. So I hope this is a simple problem that I have explained you. Now I have a question to ask you. So now I have been given, so you have been given here. This is a bit complex. So it involves application bit problem. So now what you do here is, here Suresh needs to perform a 6 task, namely P, Q, R, S, T. So basically, see, your DAG tells you what, like let's say if you have so many tasks, let's say some 5 tasks or 6 tasks, so you would have seen even the professor was telling that if you want to prioritize your task, like some tasks are dependent on the previous task, right? So until or unless the previous task is done, you cannot do the other task. For an example, if you want to do maths 2, you have to necessarily do maths 1, right? Or right, so that is something, a prerequisite, isn't it? Or let's say if you want to do machine learning, then you must do maths 2 and stats 2. But you see that match 2 can be done only when match 1 is done, right? Similarly, when you want to do stats 2, then stats 1 has to be done, right? So you see this is what dependency thing is, right? So whenever you have a task dependency thing, then you go with this DAG kind of problem, and there the topological sequence tells you that, okay, this is something you have to do first, then you'll have to go with this task, then you have to go with this task and this, and then finally task D, as you have seen, first A, B, C, D, right? So we got that sequence, right? It indicates that task A has to be completed first, then B, then C, and then D, right? I hope you understand that now. So likewise, we have a task-based problem here. Suresh needs to perform a 6 task, namely P, Q, R, S, T, and U, right? So some task needs to be performed after performing a particular task. That means if you want to perform this task, that is Q and R, then necessarily you will first have to perform this P. Okay. Similarly, when you want to perform this task Q, the prerequisite is you must do this task R prior. Okay. I hope you understand this. So it's this thing. That's all. So now the question to you is, what is the maximum, what is the possible order in which the Suresh can perform the task? Now it's the same thing. It's been asked like this. So enter the letters in an order separated by a comma. So that is something we'll have to do. Maybe you can take another 2-3 minutes and solve. Maybe I think 4 minutes. So 48, 49. So you can take till 53 and solve this.
Excuse me, sir. Can we give multiple answers?
Yes, yes.
Okay, sir. Thank you.
So as of now, 14 of you have given response. You need some more time or you need some hint?
It's done.
Some more times. So it's done.
All right. So do any of you need any more time? No, right?
No, sir.
Okay. So Abdullah says Q P R S U T Q P Q R E S U S T. Okay. So let's check this. So T S U E Q R. Okay. Let's see this. Okay. P U R Q S T. Okay, not possible. Okay, let's see then how it's happening, and then you can check yourself. I guess I cannot see all of yours, and I don't think so I can see your name as well here. So, but let's see what are the popular answers. So that's the popular answer. So let's see what is the approach for this. So could anyone like to answer this except Abdullah? Who is it? Shreya. Okay. Yeah, Shreya, please. You lowered hand. All right. So let me explain then. No problem. So okay. So I can take you to the solution. So you see this. It was asking was since it's a task dependency problem. So certainly this is topological sequence problem, right? So you see this Q and R task can be done only when P is done, right? Similarly, for doing task Q, I mean, you can do task Q without doing any other task. That means it indicates that this could be the one without degree 0, right? So that is one hint that you can get. So similarly, look at this P thing. You can do this R. You can do this task Q once R is done, right? So this is some understanding that we have to make. All right. So now
Excuse me, sir.
Yes, yes, yes.
Sir, I forgot to unmute myself. So.
Oh, I see. Okay. So could you go ahead now?
Yes, sir.
Tell me.
Actually, I first draw the total graph and the edges according to the list, and then one by one I deducted the vertices.
Okay, perfect. So you first drew the graph and then you found out the sequence, right?
Yes.
Okay, perfect. That's the way. That's the way. Yes. So step one. So thanks, Rhea. So we represent the given data as a graph, right? Which each task represents a vertex, right? And each directed edge from vertex I to vertex J. So there will be a directed edge if I needs to be done before J, right? I hope that's very straightforward. So based on this, for example, if I want to do task B, then I have to make sure that task A is done, right? This is our example, a straightforward example. Now, based on this, you see, since this table was given to you, we'll just draw the graph for this, right? So this is what graph you get. So now let's see this, whether this graph is right or wrong. You say this, when I want to do this task P, then I have to make sure that Q and R. So now you must be thinking how to draw these graphs. Why can't we just do it in, in a one linear fashion? And why did you do it in a circular way? So you will notice that it's always good to draw, you write this vertices in a circular fashion, right? So then the graph, when you make the graph, it becomes easy. So understand this. So whenever you take these vertices in a straight line, it becomes very difficult to make the graph. So you always take the vertices in a circular manner so that you can connect the edges from to each other. So that becomes very easy. So always keep that practice with you. So you see this. So just let's confirm that whether this graph is right or wrong. So you see this. If I have to perform task Q and R, then I have to make sure that I'm doing this P, right? So you see this Q, if I have to perform this task Q, then I have to make sure that P is done first. Similarly, when I have to do this task R, then I have to make sure that P is done first, right? Now let's go with Q. So Q does not have any prior thing. For Q, it's just, there is no out degree. Basically, it has just in degrees, right? What about when you want to do Q, then you have to make sure that R is done first, right? So this is some condition like this, right? So similarly, when you want to do this P and R, then you have to make sure this S is done. So where is this P and R? So let's spot this. So P is here. So if I have to do this P, then I have to make sure that R is done first, right? So you see, sorry, the other way around. So if I have to do this P, then I have to make sure that S is done. So where is this S? So you see this. So it indicates that you see this ending points, the head and tail, right? So this tail indicates that this task has to be done prior to this task, the head, wherever this head arrow is pointing, right? So I hope that is okay. So based on this, we obtain this graph. Now, once we obtain the graph, all we have to do is what? Topological sequence. So now see here, so this was interesting, right? So you had two components to solve here. One is you have to make the graph, and then the other part was to find out the topological sequence, right? So now based on this graph, now you have to notice that this is a DAG. Now, is this really a DAG? Is there any cycle? So that is also an essential part to see, that there is no cycle, right? So whenever you make a graph, make sure that there is no cycle in that before claiming that it is a DAG, right? So you might have an option, so it's not a DAG. So you have to make sure that it's not a DAG first, right? So is this a DAG? So answer is no, it's not a DAG, because there is no cycle formations. You can see, you can consider here, you can consider here, and you can consider here as well. So you can consider the first pentagon. No, it's not a pentagon, it's a quadrilateral. So you see the first quadrilateral, there is no cycle formation. Here in this triangle, there is no cycle formation. Even here in the lower triangle, there is no cycle formation. Then you can consider the other part. Now this bigger quadrilateral, right? Even here there is nothing. So now you can take this, maybe this is three hexagon, right? So when you take this hexagon, then you see again there is no cycle formation. So it's basically DAG, right? So now if this is a DAG, then I can do topological sequencing, right? So how is that done? So first we find out the in degree of all the vertices in the graph, right? So you see that we are spotting this in degree. So it's written here in the red thing. So you see this, all these in degrees are written. So what is the in degree of T? 0. What is the in degree of S? 1. So wherever this head points, the arrow head points, that's the in degree for that vertices, right? So you see how many heads are pointing at S? It's just 1. So in degree is 1. What about how many heads are pointing at R? 2.
2.
So the in degree is 2. Similarly, how many heads are pointing at Q? 2 again. So the in degree is 2. Similarly for P, how many heads are pointing? 2. So again, the in degree is 2. For Q, it's 1, right? So which vertices should I remove first here? T. So that indicates that I must do task T first, right? This is what essentially it says, right? So I have to do first task T. So that comes in our. So you see that now we are finding the topological sequence. So vertex T has in degree 0, right? So we will first remove that T from the graph, and then we can add that to our topological sequence, right? So here you can see here at the bottom, topological sequence. In our topological sequence, I'm representing here as a T. Now once I remove that T, now I have to remove that T. So now if I remove that, what do I get? I get something like this, right? Right? Now I have two vertices. Now I have two vertices with, now what is the in degree of U? How many heads are pointing at you? 0. About, can you tell me about S? Again 0, so I'll mute all again. Okay, so how many heads are pointing at S? 0. How many heads are pointing at P? 2. These are undisturbed, right? So these are same as prior. So now you see we have 2. We can take any, right? Because I can do either this task or this task, right? So I can choose any. So now here comes the 2 sequence condition, right? So you can take either U or S. So what we have done is now vertex U and vertex S has in degree 0. So we can choose any, right? So remove any one of them, that is either U or S, from the graph and add it to the topological sequence. Suppose we remove here vertex U. So once we remove that, then we can add that to our topological sequence, right? So now in my topological sequence, I have T and U. Note that I can have a different topological sequence, which is starting with T and then you will have S, right? You can have that. So maybe we'll see that sequence, what that sequence is. I hope you have worked out and you get that, right? So now we update the in degree of each of the remaining vertices in the graph, right? So when you do that, so you get something graph like this after removing U, right? So now you'll have this in degree, this is 0. Now you see the in degree of P is 1, because you see the U was pointing at P, now that is gone. And initially it has, earlier it had 2 in degrees, now it has 1. The rest 2 are undisturbed, so it's kept as it is, right? Now again, which vertex should be the next that I should remove? S, right? Are you with me?
Yes,
Yes, sir.
Yes, sir. Yes, sir.
S, why? Because it's in degrees 0, right? So if I remove that, so that I can put it in my topological sequence. Likewise, I will update the other one. So now if I remove that, now I'll be left with this. Now you see what is the in degree of P? How many heads are pointing here? 0. So in degree is 0. What about Q? 2 and R is 1. So now again, I'll start with P. Now I can remove P. If I remove P, what I'll be left with? R and Q, right? So these two edges will go off, right? Oh, sorry, these two, these two edges will go. So now let's see that now in my new topological sequence, I'll have P as well, right? Now I can add this P to my topological sequence. Now you see that now I can update the in degrees for the remaining vertices in the graph. So once I do that, then I'll be left with R and Q. So now you see this is again a topological sequence, isn't it? So now I can remove, which should I remove? R or Q?
R.
If I remove R, then I can update this in my topological sequence, and the last
And
one
Q.
which is left, Q. So I can just add it, right? So the topological sequence is T, U, S, P, R, Q. So the order of performing my task should be that first I should do T, then I can do U, I can do S, P, Q, R, and Q, right? So that's one sequence. Hence, we should perform the task in an order this, right?
Yeah.
Okay. Note, this topological sequence is not unique, right? So as we figured it out initial, you see after T, we land up with S and U, both had in degree 0, right? So we can either choose U or S. That was the condition, right? So we chose U and then we move ahead, right? So when you choose S, then you will get the sequence like this. So T, S, U, P, R, Q. So this is another topological sequence, right? So you can do the task in this order as well, right? Right? So these are the two sequences which you obtain. All right.
Excuse me, sir. Can we go to the question?
Yeah. Okay, so I have to go to.
Sir, is that like we have to give the answer, like two answers?
Yes. You have to give two answers. So it's basically you will have been given options. Okay. Since it's MSQ, so we have privilege to give you two, right?
Okay.
Yeah. So you want to know that question, right? Somebody asked me. Yes.
Yes, sir. This is Abdullah. Actually, how can we do the first T, sir? Because we have prerequisite of U and S for that. So how can I first take the?
That's what, like you first have to make, you have to do this by drawing the graph, right? So when you drew this, now you see that when you see at the graph, we just look at the graph, okay? Where we do that graph, right? No, it says you can do, so if you go at T, you see nowhere you see T here. It says what? When you want to do U and S, right? When you want to do U and S, then make sure that you are doing T. Do you have T here in the second column? Anywhere, see. T is not dependent on any of the earlier tasks.
I think I misunderstood the question.
Yes. I was repeating this 2-3 times, but it's okay, no problem. Once you understand that, right, you will get it. I hope that's okay. So any more doubts here? No doubt? If you, okay. So this is all for today's thing. I have some more question to discuss. So maybe somebody asked me in the very beginning how to do, the DFS tree, BFS tree, right? Right?
Okay.
Yeah.
Yes,
so this is all for today's session. You may leave. Those who want to stay with me, I can explain you that. Yes.
Hello, sir. Related to DAG, there is a question in activity 10.9.
Okay.
Sir, I didn't understand this one.
Okay, so maybe one of us can help out here to you to solve that. So maybe I can just open that. And then we can quickly go to our. Which one?
10.9.
Yeah. Which question?
Sir, first question.
Okay. Yeah. So maybe like any of you can try assist him. Yes. Can you tell me what was your doubt here?
Sir, I didn't understand the question.
You didn't understand the question. Okay. So the entry and its dependencies in a shell for any spreadsheet it's similar to what we have done, right?
Yes, sir. I understand that question which you tell. But this what column, this A, B, I didn't understand the A1, A2.
Okay. Okay, so maybe we can just see that. So what is this A1 square? So maybe I can just, the entry A1 square in the cell B1 means in cell B1, the entry and its dependencies in a cell for a spreadsheet can be represented using a directed acyclic graph shown in this. Shows a small part in the spreadsheet. The particular cell in the spreadsheet can be represented as xi. Okay, where x represents the column and I represents the rows. Okay, the entry A1 square in shell B1 means B1 has the value A1 square, where A1 is the value in the column A row 1. Okay, so would anyone like to explain this?
Sir, in this question, A1 square means the value of row 1, column 1 ka square, A1 ka square. What is the value of A1? That is the value of square of B1.
Okay. Okay. What about this entry number row 3? What is this B2 slash A3?
The value of B2 divided by value of A3. A3 is A2 plus B2.
Okay. What about this A1 square? How did you tell this?
The value of A1 ka square. What is the value of A1?
Okay. So what is the value of A1 here? A1. Okay, so if this is the case, then how do you attempt this question? First question.
Not do that one.
Okay, so would anyone like to explain this? Anyone else? Okay, nobody. So maybe like even I have to look into this part. I haven't solved this. So here you say is that A1 is A1 square and B1 minus 10, so it's B2. So A1 square and B1 minus 10 is B2 and A2 plus B2 is B2 minus A3. So sorry, what's your good name? Who asked me this question?
Sir, Shivam Thavilyal.
Shivam, so maybe you can just give me some time. Maybe I can take up this at end, or sometime I can explain you in the discourse itself. Okay.
Okay, sir.
Is that okay? Yeah.
Sir, I also asked this question in the disclosure, but someone
okay,
give
fine.
the
Then,
answer. Okay, sir.
Okay.
You can take time.
Okay. I'll take that. Maybe I'll have to go through this. Okay, and then explain you this. All right. Yeah.
Okay.
So yes, I had this part. So let's go with this one. So here BFS tree, right? So yes, so this is similar to what we were doing, like how many of, so I don't think so we have to discuss this question because I think you can answer this is like direct like that. So BFS tree in topological sequence. Okay, so let's try one more questions on topological sequence. Okay, so now you have this DAG given to you. Could you tell me which is the topological sequence for this? Quickly.
FCB.
Okay.
It's E, F, C, E.
Okay, so I can see in the chat window of this thing, somebody is asking what is this forward edges, backward edges, and cross edges. So maybe we can discuss here in this particular question. So you can just see this. So all right. So yeah,
Third one.
third one is right. Okay. What about
fourth one? Can also be right.
Fourth one can also be right. So third and fourth. So you see, this is third and fourth are actually right answer for this. So how is this done, right? So we can just see. You can see this. So this is a DAG problem. So you see this, you first have to do what? Again, you list it in degrees, right? So what is in degree of E? 0. What is in degree of F? 1. How many heads are pointing at D?
3.
1, 3, again 3, 2, 2. Okay, so now I'll have to remove this E. So do I have E here? So E is there for all, F is there for all. So if I remove this, then this is gone, then this is gone, and this is gone, and I can strike off this, right? Now I'll update my in degrees. I hope that is okay. I know I should do it in the way around. I should draw a different graph, but I don't want to draw a different graph. I just want to explain you here, suppose. So what is the in degree of F now? I'll update the others. So, what is in degree of F?
0.
What is in degree of 2? B, 2. What is in degree of A?
2.
That's all. These were the only 3 vertices which E could have affected, right? So these are the thing. Now I have, so I can just write it my sequence E. Now what about F? Now F has in degree 0. So now I can cut this. If I am doing, these are the 2 vertices which it will affect, right? 3 vertices in fact. So which are those 3? This, this, and this. Now what is in degree of? So I'll change in degrees for this. What is in degree of D?
2.
2. What is in degree of C?
0.
Yeah, 0. So now this is okay. So just a minute. Yeah. So I guess my pen is not writing. Just give me a minute. So what is its in degree?
C is 0.
Okay. C is 0. Now what about B?
B is 1.
B is 1. The rest remains same because we saw only these were affecting, right? Now similarly, if I am at C, what else I can do? Now this is the other thing. So now what are now E? What was this vertex? F, right? So F, and then which is the other one? Now C is something I'm omitting, right? So C comes in my topological sequence, right? So E, F, C came here. So now you see that now which one should I remove? Since I'm doing this, then I'm essentially affecting this one, and this one. So I have to make changes at these vertices, right? Yes. So now you see this becomes 0. So what is in degree of this now?
1.
What is in degree of H?
H is 1.
What is in degree of G?
1.
And notice even this is affecting this as well, right? Right. So there were 4 vertices which it was connected to, isn't it?
Yes.
Or it was directed towards, right? So now in degree for this also is
0.
So now I have what? B in my sequence because this has got in degree 0. Now I'll cut this, cross it. So now I'll see that this is being affected and this is being affected, right? So I'll make changes over here. So what is in degree of G?
0.
What is in degree of A? 1. What is in degree of H? H remains the same, right? So there is no more changes. So now what? Now I'll deal with this G, right? So now I'll just cut this. So maybe I could, yeah. So I can just cut this G. So if I do this, this was only affecting, so this was affecting this and this, right? So now I can have cross this and this. So now what is in degree of A? 0. What is in degree of H?
0.
0. So now I have 2s with the zeros. Now comes the thing. So now I can go with either A. So if I go with A, then what happens? I went with A, then it was not affecting any. So I can go with what next?
H.
So I can go with H here as well, right? So that is also something I have to keep it in my mind. So I'll just have another sequence. This remains the same. So now next I'll go with, now I'll complete this sequence. I go to the H, then D, right? Because if I go to H, So if I cross this H, then this D, the D remains, the D comes in. Now if I go with H, then what happens? If I go with H, the A remains as it is. So if I say H, H, A, D or H, D, A is also possible, right? Because if I go with H, this will become 0, this will also become 0. So I can take either this or this, right? So these are the three sequences which we can have, right? Okay, so which are those which has been given? So this and this was given. So this is given. So you see, this is one way of doing it in your exams. You can practice like this. Now let's go with now consider this is not a DAG problem. Now we understood how to do, sorry, this is we got this sequence, topological sequence. Now consider this is essentially not a DAG problem. Suppose I want to draw the BFS tree for this. Now we'll do this BFS and DFS problem here itself. Okay, so could you tell me what is how do we draw the BFS tree, right? Or DFS tree. So first we will do the DFS tree for this. Okay, so how do we do this? So you visit and then you explore. These are the only two keywords we have to keep it in our mind. Okay, so now let's say you visit somewhere from E. Okay, so that's my root vertex. Let's say I'm building my DFS from my root vertex. Root vertex is E. Okay, so if I start with E, now I visit E. So which are the things which I should be exploring then? These are the two things, A and F. Okay, so I can explore any of these, but we will go in an alphabetical order. Okay, so now I'll be exploring A. So you see in DFS what happens? You do depth search, right? So after A, where all you can go, right? You see, from A, can you go anywhere else?
No.
I cannot go anywhere else. So sir was telling something about pre-counter and post-counter, right? So that is something you can always practice with, but let's not, I'm not writing, let's say I'm not writing this pre and post, and I simply just want to go. It's essentially the same thing, but I'm not writing it. Now from A, I cannot go anywhere. So I backtrack, right? I backtrack to E. Now again, I will ask myself, from E, can I go anywhere else? The answer is yes, I can go to F, right? So essentially sir was telling, the professor was telling about pre and post numbering, right? That is certainly very important thing, which you should practice like that. But since I'm just talking about how to draw the DFS tree, so I'm not writing that, but essentially I'm doing it that, right? So now you see this from F, where all I can go. Now I'm doing depth first. Yes, yes.
Sir, from E, we can also go to B.
That's right. We can go to all three of these. We'll come to this. Now I'm telling, okay, so since we are talking about, we should go in an order. So let's go in the order. Okay, so let's go in an alphabetical order. So from A, I can go to where? So now I have visited. So which all I visit, I'll mark them. Okay, so from E, I have visited A, and I see from A, I cannot go anywhere, right? So I backtrack to E. Now from E, can I go anywhere? In an alphabetical order. So which is the least one? B. I can go to B, right? So now I'll say, okay, I'll go to B. So that comes the next one. So you see from here, I backtracked, and then from E, I'm going to B, right? From B, can I go anywhere?
Yes, sir. A and G.
Where? I can go to A. And I can go to G. Right? Yes. So let's say I go to G. All right. So when I go to, so I have visited what? I have visited B. I have visited G. Right? Okay. From G, can I go anywhere?
H.
I can go to H. So I can just write down H here. Okay. So I visited H as well. From H, can I go anywhere?
D.
I can go to D. That is something I can write. So I have visited D as well. Now I'll come back from D to H. From H, can I go anywhere? Anywhere else apart from D?
No.
From H, can I, sorry, now I'll go again, backtrack this. From G, can I go anywhere else? I can go to A, but A is already visited, so I don't have to go there again. Right? So then I'll go back to my original one. From where did I come? G to B, right? So from B, I came here, right? So I cannot go to anywhere. These are only two places where I can go, right? So I'm not interested in going anywhere else. I mean, I cannot go anywhere else. It's not about my interest or something, right? So now I go back to B. From B, can I go to anywhere? From B, I went to G, right? From B, can I go anywhere? Yes, I can go to A. right? I can go to A, but A is already visited, so nothing much can be done, right? So just avoid that. Now again I backtrack. If I backtrack from here, I'll go back to E. So from E, can I go anywhere?
Yes, you have.
F. So I can go to F. So let's say I go to F. I write it here. So let's say I'm giving this F. All right. So from F, can I go anywhere else?
C.
I can go to D, C, and B, but these two are already visited, so I'm not interested. So no need to visit again. So I can go to C. So from here, I can go to C. From C, can I go anywhere? I don't have to go anywhere because I have visited all these vertices. So this is my DFS tree. Okay. Now the concepts. Now you see how many edges do I have here? 1, 2, 3, 4, 5, 6, 7. So how many edges do I have in my DFS tree? 7 edges. And these edges are called as forward edges.
Okay.
Right? So how many forward edges do I have?
7.
Okay. So these are some terminologies. So forward edges are 7. Okay. So forward edges are 7. Now, what are the, so in my original graphs, how many vertices, how many edges do I had? So just let's count it totally. I'll just mute all. Okay, so how many edges do I had? So 1, 2, 3, 4, 5. So maybe 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I had 15. Okay. So then in my BFS tree, so this is basically my DFS tree, right? So I obtained my DFS tree. In my DFS tree, I had 7 edges, right? Forward edges. Now, what about the remaining edges? What do we call them? So there is some other words. There is something called back edges, and there is something called cross edges. Okay, so let's see what are these. Okay, so now you see this from E. You see, have I covered all the edges? The answer is yes. This is all covered. Now let's look at the other edges that I have covered. So I have covered this, and this is covered in my DFS tree, right? Right? Okay. So now from A to B, from B to A, there is an edge. Right? From B to A, right? So maybe I can use a different color. Maybe I can use green color. So you see this, there is an edge here, B to A, right? So I can cross this. This is also covered, right? Now you look at this. Is there any edges? Any more edges as such? Maybe I can use
G to A is there.
Okay, so what about G to A? Huh? So what about G to A? Do I have?
That's a cross edge, I think.
Okay, so maybe we can mark all these forward edges in our tree, and then we can look at the other edges, right? So now, which are all the forward edges? Now, BG, is there a BG? B and G. Okay, so this is marked. What about G and H? G and H is also marked. Okay. What about H and D? So H and D is also marked. Now these are the one which I'm marking here with this red color are forward edges, right? Okay. And what about FC, FC? FC is here. So these are the forward edges, right? So forward edges are 7. Now let's see the other edges that I can have. So here, so maybe then I can go with this backward edges, and maybe not backward edges, but let's see which are these edges, and we can just mark them. Okay. So now I have this BA. Okay. So I have marked this here. Now, which are the other one? Okay. So what about this CB? CB.
Yes,
CB. Okay. So CB is here.
FB also.
Okay. So this is also marked. What about
CD?
CD. Okay. We can go with CD. So let's see. Where is the CD?
And
CD. It's here.
And FD?
FD, right? Okay. So FD is here. So F and D. Oh, this long path. Okay. Something like this. FD.
And FB?
FB. Okay. Where is it? Yes. FB. So FB. Yes.
CG. CG?
CG, right?
Yeah.
Okay. So where is this C and G? Okay, yeah, it's here. CG.
C
So
and H.
CG. Okay, so CG is here. C to G it is, right? Yeah.
GA.
And GA. So where is this? GA? It's here.
CN.
Okay. Okay. So you notice this. You notice this. All these edges which we have drawn. Now you see there is how many branches do we have here in this DFS tree? There are 3 branches. One. This is another one. And this is another one. You can see there are 3 branches here. All right. Now you see this. What are these back edges? So could you tell me how many back edges do I have here?
5.
Can we see 3?
7.
7.
7.
6.
5.
Think, tell me how many back edges do I have?
2.
Or do I have any back edges?
Back to like G to A and C to B.
Just check, do we have any back edges? I don't
we
think
don't
so.
have
There is
any.
any back edges. The back edges are 0.
What are back edges? Just
I'll come to this. What do you mean by cross edges? So the remaining are cross edges. So how many cross edges do we have? 1, 2, 3, 4, 5, 6,
7.
7, 8.
8.
8. Because totally 15 we had, right? So 8. So what are these back edges? Now you understood there are 3 trees here, right? This is one tree. This is another tree. This is another tree. Okay. And what are these cross edges? Cross edges are, you have the edges apart from these forward edges, you have another edges which are interconnecting between the 2 branches. Now you see all these edges are interconnecting between 2 different branches, isn't it? Okay, so what is then this back edges? Back edges are those edges which happens on the same branch. Which happens on the same branch. Okay, am I clear on this? Am I clear on this?
Yes.
Okay. So now when can we add it? If I had an edge, something like this. Okay. And I had something like this, then this would have been a back edge because this is on the same tree. Which is that tree? Which is on same branch, I mean. So this is that branch, E, B, G, H, D. So something like this kind of edges forms a back edges. Okay. Yeah.
Excuse me, sir. Cross edges and back edges are independent, right? Independent of each other.
Yes.
Sir, explain the cross edges.
Cross edges. So see, you see this edge, right? You see this edge. This edge is happening on the same tree or 2 different trees? 2 different trees.
2 different branches.
Oh, sorry, 2 different branches. Since this is happening on 2 different branches, therefore it is a cross edge. Okay. Okay, clear.
And it comes 7, right? And you said like it is 8.
1, 2, 3, 4, 5, 6, 7. Okay, yeah, it's 7.
No, sir. Between C and H, you forget.
Between C and H. Oh, I did not give that. Between C and H. Oh, yeah, I have forgotten here.
Yes.
There was one more. Yes. Thanks for pointing. So between C and H, there is another edge.
Yeah.
Okay, thanks for pointing that. Okay, so now you see this. Now we understood what are forward edges, backward edges, cross edges. All right. Okay. So this is all for today's thing. Today's session. So you understood how to draw this BFS. Okay, I missed one more thing. I did not do DFS tree, so maybe I can BFS tree. So you know that in DFS tree, what are we doing? You take any one edge and then you go in depth. You search all other things, right? But how do we do this BFS search, right? So let's do that BFS search as well.
Can you explain one more time back edge?
Okay, back edge. Back edge is okay. So back edge is you will have another edge. You will have another backward. You will have another backward edge. Okay, on the same branch. So that means you will have something like this. This is one branch.
Okay.
Got it? Okay.
Yes.
Okay. So I hope that is okay. So now this was about DFS tree. So similarly, let's do for BFS tree. Okay. So how do we do that BFS tree, right?
So can we say that back edges will only form cycles?
Yes. You can say that. Yes, you can say that. Okay. So now let's do this BFS tree now. So now again, we'll do the same way. All right. So maybe just for the change, or just keep it like that. Again, our root node is E. Okay. So our root node is E. From E, where all can I go?
I can go to E, N, F, B.
I can go to A. I can go to B. I can go to
F.
These are the 3 places I can go. Right. Now, what we do here in BFS tree is, now this is level 0. Okay. You know that this is level 1. We're just giving it a level 1. Now what? You will search for A. From A, can you go anywhere? You cannot go anywhere. What about from B? This is it. From B, where all you can go? You can go to
A and G.
You can go to A and G, right? So this is the next thing I can go. So this is G. I will write it here, right? From F, where all I can go?
B, C, and D.
Okay. From F, I can go to
B,
C, and D. So I can go to C. Yes, I can go to D. These are the 2 places I can go, right? Now notice this. I'm not searching what is happening after D. I'm going in an order, right? Right. So I'm doing it level by level. In other words, if I have to draw this Q thing, let's say if I had it E in my first entry, like when I visit E, then I explore its neighbors, right? So my neighbors are A,
B,
F. So what did I do? Then what do I do? Then I first, is there any more thing I can do? So no. So if I cannot do this, then I can exit this. If I exit this, E is gone. Now permanently E is gone. But in your DFS, it was suspended, right? You can always bring in E. That is what we were doing it in your DFS, right? Now what? We will look at A. From A, where all I can go? I cannot go anywhere. So no more entries will come in here. So A will exit, right? From B, I can go to G. So G comes in my entry, right? And G exits, right? From F, where all I can go? I can go to C and D. So F is gone again. F role is gone. Now next entry is G. From G, I will look. From G, where all I can go?
H.
I can go to H. So H comes in my entry here. So G is out. I can go to A as well, but A is already visited. So it's no need to visit again. Now I will go to C. From C, where all I can go?
G,
H. And no need to go to any other places. So sorry, H is already visited, right?
Yes.
No, H is not visited, but yeah, actually from C, where all I can go? I can go to H, but H is already here, so no need to go again there. Now what about C? C again I cannot do because H is already visited, so you cannot do anything about it. What about D? From D, again you are not able to go anywhere, so it's gone. Exit. What about H? From H you can go to D, but D is already visited, so again out. So this is what you get.
Sir, in this graph, G to H, rather than G to H, I can also write C to H.
No, you cannot do that because you are following this. You see this? Okay. Actually, again, you can do that depending on the sequence, like what sequence you follow. Right? Here, in this particular sequence, you cannot do that. Because you see, you have to exit in an order. It's like first in, first out. Okay. Right? First in, first out. Because whichever comes first, that has to go out. But in DFS, what we were doing it, you give the entry, but whatever was the last entry, that was going out. Isn't it? I was telling you, right?
Okay.
From here, I was going back and then I was seeing if I can go any other places. Isn't it? That's what we were doing. All right. So this is how you build BFS tree. I hope this is okay. All right. So this is all for today's session. And one thing that I have to look into is that activity question that is on 10, the one which I have to look for. I did not go through that once. Maybe I need some more attention to see that. All right. So thank you all. This is all for today's
Sir,
presentation.
one
Sir?
second.
Yeah.
Sir, after this week 10, we'll have a revision. I mean, we'll have for week 11. And then when is our revision session is going to start, sir?
Okay. Once this week 11 is completed, now for week 11, you will have another 3 sessions. So again, activity, and you will have it on. So you will have 3 sessions for this. And then at the end, you will have
Just one more week is left after the week.
right.
11.
So first we will complete week 11 and then we will have revision session.
Okay.
Sir,
Okay.
one more
Thank
thing,
you,
sir.
sir.
Sir, when will the quiz 2 result out?
Quiz, sorry, what?
Quiz 2 results.
Quiz 2 will be announced soon, and I could see like 62% in set 1 have passed and some 82% in set 2. Yeah. So this is the number.
So
Usually it's
what was the percentage?
82.
Okay.
It's just because they had got one question which
The
was
equation.
typo.
Yeah,
And
that greater than, lesser than.
yeah. You see, there is a lot of difference, and it has got a higher weightage.
Yeah, three problem.
You had a 3
on it,
problem.
yeah.
Like,
3-3-2 something are the
so
mark.
they're lucky. So you can say that.
But it is actually in order, sir. So
Actually,
we called
yes,
it.
there were like only few. It's like usually what happens in both the sets, there is no much variations. It's the same. We don't have to normalize or anything. It's just the same percentage. Like say in set 1, if 62 passed, then in set 2 it will be like 62 point something or like 61 or 63. So not much deviations. But here it's just because of that there is a lot of deviation, and we cannot even say that those who can score 0 or who did not even attempt to give them marks or like whatever. So we just did not wanted to do this because some or the other person would have claimed something. So we thought like, okay, we can just give full marks to all because it was typo from our end.
So one more thing. Sir, what is the weightage for the end term exam? It is same 40%.
Okay, so if you are to ask me, yeah, I'll tell you that for end term exam. So it's just roughly I'm telling you. I know we will formally announce this. So it's just this. You have to keep it in your mind is generally these. You can say that week 7, 8, 9, 10, 11. Okay, they have like 60% of weightage. 60. Okay. And then week 1 to 5, week 1 to 6 will have 40% of it. Okay, so if you have to ask me, focus more on this part, this thing, your calculus, graph theory, because this has got slighter weightage, but you see there is not much difference as I'm telling you, right? So week 1 to 6, you will have 40% of your weightage, and 7 to your 11 will have 60% of your weightage. Because essentially you see in the earlier weeks, it's just a straight line, quadratic and polynomials, right? It's essentially the same, right? It's not much to be asked. And we did not ask much questions from graph theory, right? So this is where we can check your knowledge, and this is something scoring, so you can score.
From week 1 to 6, it will be one set problem, one SSD.
Right. So you can, so you see this week 1 to 6, you can, if you have to put it in a basket, you can say that week 1 to 6 is one basket. Week 7, 8, 9 is another basket of calculus. Okay. And graph theory is week 11 to 12. Week 10 and 11. So you have 3 baskets. So maybe we can just come up with a way wherein we can actually formalize and tell you, okay, the first basket contains this much percentage. So as I told you, it's 40%. Second basket might be something, that is something I don't know. But merging basket number 2 and 3, you have 60% of your weighting.
So one last question, sir. And sir, what is the calculation of the final score?
Calculation
of
the
quiz 1, quiz 2, and the end term.
Okay, so that is something you will have to look for, but the maximum weightage is given for your end term. I think, I don't know the distribution for that. Maybe you can ask your colleagues, your friends.
You can check the discourse if you are there in the discourse.
If
not, I mean, it is little difficult to explain without that. If you want, I can explain in a minute. Explain.
If you want it, you want it now, or you want to go through the discourse and read it once?
If he's on discourse, let him do over there. It would be more better.
Yeah. I think that will be worth reading. Just go to discourse and read it. I think that is okay. Okay. So this is all. All right. So you see, this was our last session for week 10. So week 11, it is something you have more concepts coming in, wherein you will have algorithm based questions. So you have so many algorithms. So you have Dijkstra, you have Floyd-Warshall, then you have Bellman-Ford, then you have Prim's algorithm, Kruskal's algorithm. So there are so many algorithms, and all of them are very important. Its applications are important. And you also have matrices, multiplications, and all this. So there are so many concepts in week 12. Okay. So do pay attention to that particular week. Okay. Even this was important because so many things are here as well. But that is more of, more of algorithm based. So it's really good to go through the lectures and understand the thing what Search is, right? And anyways, we will take the live sessions. We can take up your doubt. Okay. So this is all for today's session. Yeah.
Thank you, sir. Thank you so much.
Yeah. Thank you. Thank you. Then we can end our session.
Good night.
Good night.
Thank you. Good night.
Yeah. Good night.
Thank you very much, sir.
Yeah.
Good night.
Good night. All.